In this video, I'm going to talk about graphs of other trig functions besides the ones we've already talked about. We talked about cosine and sine, and today we're going to talk about tangent, cotangent, secant, and cosecant. We're going to start with tangent. And I know the equation that I'm going to use for tangent is y is equal to tangent of x. Another way that I could write this is y is equal to sine of x over cosine of x. So this is just something that you need to know. Tangent is also equivalent to sine over cosine. Remember when we were looking at the unit circle, if we wanted to find tangent, we did the y coordinate over the x coordinate on the unit circle. So we did sine over cosine. So this is another way that I can write this equation. Using that, I know that for the tangent graph, I need to keep in mind that cosine of x cannot be equal to 0. So something I need to keep in mind is that cosine of x cannot be equal to 0 because that would make the denominator equal to 0. So that would make the denominator equal to 0 if cosine was 0. So whenever cosine of x is equal to 0, there is a vertical asymptote. Back to what we did with rational functions. I know that whatever's in the denominator after I simplified, this is as simplified as I can make it, makes a vertical asymptote because there is a break at that x value. So for the x values that I could plug in, talking about radians, for the x values I could plug in for x that would make cosine 0, those are plus or minus pi over 2, plus or minus 3 pi over 2. We talked about this before. Plus or minus 5 pi over 2, and the pattern continues. Plus or minus 7 pi over 2, etc. So I'll have vertical asymptotes at x is equal to pi over 2, x is equal to negative pi over 2, x is equal to 3 pi over 2, x is equal to negative 3 pi over 2. The other thing that I want to keep in mind is, or the other thing that's going to help me graph this, is thinking about what would make, or how I would get x-intercepts. So that's when the numerator would be equal to 0. That's when sine would be equal to 0 here. So when sine is equal to 0, sine of x is equal to 0, comma. Why did I say comma? You have x-intercepts. So you have x-intercepts, or zeros. And those are going to be at, so sine of 0 is 0, sine of plus or minus pi is 0, sine of plus or minus 2 pi is 0, sine of plus or minus 3 pi, and that pattern continues, plus or minus 4 pi, dot, dot, dot. These values are halfway in between, the two asymptotes on either side. So it's halfway, the y-intercepts are halfway between the asymptotes. Just something to keep in mind to help you graph when you do not have, this is the parent function that we're talking about, so when you don't have the parent function, you know your x-intercepts are going to be halfway in between the asymptotes. That's another way you can think about it. The other thing I want to think about is, so I'm thinking about the unit circle for the parent function. I know that the amplitude is 1 because it's based off of the unit circle, which its radius is 1. So if I think about the unit circle, halfway between 0, the 0 that I have, or the x-intercept that I have, and the asymptote is a reference 45 degree angle. 45 degree angle. I know it's like halfway in between pi over 2 and pi over 2 and 0 is pi over 4, which is a 45 degree angle. All of them are a reference 45 degree angles in between, in the middle. And cosine of theta and sine of theta for 45 degree reference angles are plus or minus square root of 2 over 2. And so I know that tangent of theta, if I put square root of 2 over 2 over square root of 2 over 2, or square root of 2 over 2 over negative square root of 2, whichever way I do it, I either get I get one of two answers for tangent, which is plus or minus 1, since they're the same at the top and the bottom. Something I also want to keep in mind when I'm writing tangent graphs or drawing tangent graphs is that a period is equal to pi over 6. So from asymptote to asymptote, the distance, the horizontal distance is not over 6. Why did I say that? That's over b. Pi over b is the horizontal distance between asymptote to asymptote for a tangent function. I also want to keep in mind that one cycle is from negative pi over 2b to pi over 2b. So this is one cycle. So the period I need to know from asymptote to asymptote is pi over b. That's the horizontal length of the period. One cycle is from negative pi over 2b to pi over 2b. And then the other thing I want to know, or I need to know, is that the vertical asymptotes are at the end of each cycle. Okay. And now I'm going to actually graph tangent. I'm going to actually graph the tangent graph. I'm going to actually start this more in the middle. So here is good. And then I'll draw like this. It's not great. I'm going to count by pi over 2. So this is pi over 2. This will be 3 pi over 2. No, what? This will be pi. This will be 3 pi over 2. This will be 2 pi. This will be 5 pi over 2. 3 pi. And then 7 pi over 2, etc. This is negative pi over 2. This is negative pi. This is negative 3 pi over 2. That's enough. And then I'm going to draw my vertical asymptotes. So I want to draw all the vertical asymptotes that I have. Those are at these values, where cosine, where the denominator for this function would be 0. So I have a vertical asymptote here. I have a vertical asymptote here at 3 pi over 2. I have a vertical asymptote at 5 pi over 2 and 7 pi over 2. I also have one at negative pi over 2 and negative 3 pi over 2. And then I'm going to draw my x-intercepts. So those are going to be important points that I can grab from in the middle of two of my asymptotes. So I know that that's when sine is equal to 0. So that's for these values here. Those are my x-intercepts. So I have a 0, 0. I have 0 comma pi. I'm sorry, pi comma 0, 2 pi comma 0, 3 pi comma 0. I have one at negative pi comma 0. And those are, as you can see, halfway in between the two asymptotes, which is going to help you graph something that has a transformation and isn't just the parent function of tangent. The other thing, the last thing, thinking about the unit circle, if I'm halfway in between, so if I'm halfway in between 0, this point 0, and pi over 2, if I'm halfway in between that, I am at pi over 4. And I know for pi over 4, that's a 45-degree angle, and I know that cosine and sine are both square root of 2 over 2, square root of 2 over 2. If I put those on top of each other, I get 1. So I'm going to be here at this point. And then for tangent, I know that tangent is a, a odd function. So if pi over 4 is positive 1, then negative pi over 4 would be negative 1, and I should erase that so I could fit it, would be negative 1. For negative pi over 4, it would be negative 1 instead of positive 1, since it's going to be the opposite. And then I am going to connect these points like this. So these are important points that you need to include. They are also going to be the, sorry. Oh, Danny, hold on. Sorry, I'm So this is what every section of the tangent graph is going to look like. I'm going to have, on the right-hand side, so I'm going to be going down to up. I'm going to have these points. These important points are also based on my, the amplitude. So whatever the amplitude is, that's going to tell you what this point is. So if the amplitude is 1, then you have a point halfway in between the x-intercept and the asymptote at +1 or -1. If the amplitude was 3, you would have that important point at +3 and -3. And for tangent, you are going from the bottom to the top. Unless there is a reflection over the x-axis, then you would flip it upside down. Or you would flip it, so it would be going, as I go left to right, it would be going up to down. But all of these are going to look like this. So halfway in between 3 pi over 2 and 2 pi, I'm going to be at -1. Halfway in between 2 pi and 5 pi over 2, I'm going to be at +1, like this. And I'm going to keep doing that. And I connect them in curves, and those asymptotes, I'm approaching them as I get closer and closer to them. Like, you can plug in values that are super close to -3 pi over 2, and you'll see that you're going to get a very, very negative number that's going towards infinity. And then same thing as you go, if you pick a number that's just a little bit less than -3 pi over 2, you're going to see it's a really positive number if you plug that in for tangent. And that's what the tangent graph looks like. Let's do an example with a transformation. So doing an example with a transformation, maybe I have the equation y is equal to 2 tangent of 3x. And I want to label everything that's important from this equation. The first thing I know is that the amplitude is equal to 2. That's something I need to keep in mind, because that's going to tell me these important points. The b I know here is, the b is the coefficient for what's inside of tangent, so that's 3. And I'm going to use that to find the period. So I know the period is equal to pi over b, or in this case, pi over 3. And that's the period. And I'm going to use the period being pi over 3 to find what the asymptotes would be. The asymptotes here, they would be, I know I'm using this. One cycle is from -pi over 2b to pi over 2b. So I would do -pi over 2b would be 6 to pi over, I'm sorry, I don't want to say 2. I have one asymptote as x is equal to -pi over 6, and the other one is x is equal to pi over 6. So these are my asymptotes, just one of them, and then I will find the other ones after graphing. So I have, here's my graph. I'm going to be counting now by pi over 6. So I'm going to count by pi over 6 instead of pi over 2. Pi over 6, and then I'll have pi over 3. That's 2 pi over 6. And then 3 pi over 6 would be pi over 2. And then 4 pi over 6 would be 2 pi over 3. And then 5 pi over 6 would be 5 pi over 6. On the other side, I would have -pi over 6. I'd have -pi over 3. I'd have -pi over 2. And then I'm going to put in my asymptotes. So all the asymptotes, well, the first two that I'm going to graph are pi over 6 and -pi over 6. And then I know that I skip pi over 3, and I'm going to pi over 2 next. Oops. I skip 2 pi over 3, and I'm going to 5 pi over 6. On the other side, I'm skipping -pi over 3, and I'm going to -pi over 2. And you can check this in your calculator, because you can use a scientific calculator on the test, as long as it doesn't have a table function. You can actually check where your asymptotes would be for tangent, and where your sine would be. Where your x-intercepts would be. I know in the middle of the asymptotes, I have points, my x-intercepts, not just any point, but my x-intercepts are halfway in between all the asymptotes. I know that I have, the graph is going to look like this. It's going down to up. I want to know what these important points are halfway in between the asymptote and the x-intercept. I know that since my amplitude is 2, I'm going to have a point at -2 here and positive 2 here, halfway in between -pi/3 and -pi/6. So I will be connecting them like this. That's what it's going to look like here between -pi/6 and 0, 0. I'm going to have, a point at -2. Here I'll have a point at +2. I'm going downwards, upwards. Same thing here, except I keep doing 1 instead of 2. You need to make sure you're doing 2 because that's the amplitude. Here and here. And that's what my graph looks like for tangent, or 2 tangent 3x. All right. The next thing I'm going to talk about are reciprocal functions. So I'm going to talk about reciprocal functions. The first one I'm going to talk about, since we just talked about tangent, I'm going to talk about its opposite, so cotangent, or its reciprocal, cotangent. Cotangent is written like this, and I know I could also write this as, since cotangent is the reciprocal of tangent, instead of sine over cosine, it's cosine over sine. So important things that I want to keep in mind. I know that sine of x cannot be equal to 0. That would make the denominator equal to 0, and I would have vertical asymptotes based on like what we did with rational functions. When I have something that makes the denominator equal to 0, I know that I'm going to have a break at that point for x, because x is not allowed to be certain things. So if sine cannot be equal to 0, or sine of x cannot be equal to 0. So whenever sine of x is equal to 0, there is a vertical asymptote. And the vertical asymptotes for sine, the x values that would make sine equal to 0 are 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi. Those are the values that would make sine of x equal to 0. So all of these are going to be vertical asymptotes. These are all vertical asymptotes on my graph for the parent function. The other thing I need to keep in mind is when cosine of x is equal to 0, there is going to be an x-intercept. So I have plus or minus pi over 2, plus or minus 3 pi over 2. I have plus or minus 5 pi over 2, plus or minus 7 pi over 2. These are all x-intercepts. So these are all x-intercepts. Because those values for x are what would make cosine 0. And that would make this function 0. So it would make cotangent 0. Another thing to keep in mind is these are halfway. So these are halfway between 0 and the asymptote, just like they were in the tangent graph. So it looks very similar to the tangent graph. There's just different vertical asymptotes and different x-intercepts. And you're going to see one other difference, and I'll show you what it is when I graph this. So I'm going to count by pi over 2. So this is pi over 2. This is pi, 3 pi over 2, 2 pi. This is 5 pi over 2, negative pi over 2, negative pi, and then negative 3 pi over 2. And then I'm going to put all my vertical asymptotes in. And all my vertical asymptotes are x is equal to 0, x is equal to plus or minus pi. So x is equal to 0, x is equal to plus or minus pi. Plus or minus 2 pi. I don't have that on the other side, so just 2 pi, and then I'll stop there. And then, actually, I should probably continue this just a little further. So I'll do this as 3 pi and put a vertical asymptote there. And then my x-intercepts are all here. So they're when cosine will be equal to 0. So that's x is equal to pi over 2 and negative pi over 2, which notice they're halfway in between the asymptotes. It's 3 pi over 2, 5 pi over 2, those values. And then the difference between cotangent and tangent is that cotangent goes downwards as you go to the right, downwards. So in between the two, so in between 0, 0 and pi over 2, the halfway point, this is pi over 4. And if I do cotangent of pi over 4, I know that that is 1. I know that that's 1 because I have pi over 2 over 2 divided by pi over 2 over 2, and I know that's equal to 1. When I am at this value here, I am going to be at negative 1 for cotangent. And so my graph will look like this. As I go to the right, I'm getting closer and closer to that vertical asymptote. As I go to the left, I'm getting closer and closer to the vertical asymptote on the left. And I'm going to be doing that for each one. Again, for those important points on the left and right of that x-intercept, they are coming from the amplitude. They're coming from the amplitude of the graph. So this is what a cotangent graph looks like. That's what a cotangent graph looks like. The next thing I'm going to talk about is the secant graph. So secant, which is the reciprocal of cosine. I know I can write it as y is equal to secant of x, or I can write it as y is equal to 1 over cosine of x. One thing I want to keep in mind is cosine of x is not equal to 0, or sorry, why am I not thinking straight? Cosine of x cannot be equal to 0, is what I meant to say. So whenever cosine of x is equal to 0, there is a vertical asymptote for the secant graph. So there's a vertical asymptote for the secant graph. And so those are for values, let's see. So x is equal to plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2. Those are the x values that would make cosine 0. So these are all going to be vertical asymptotes. These are all vertical asymptotes on my graph. And so I'm going to graph. In order to graph these, what I'm going to do is I'm actually going to graph cosine since it's the reciprocal. And then after I graph cosine, I'm going to use it to graph what secant is. So I'm going to, my scale is pi over 2, so pi over 2, pi, 3 pi over 2, 2 pi, this is 5 pi over 2, and 3 pi, negative pi over 2, negative pi, negative 3 pi over 2. And then I'm going to put all, before I put the vertical asymptotes on, I'm going to actually graph cosine of x. So cosine of x, I know, cosine of x I have starts at, what am I doing? Oh, it starts at 0, 1, and then it goes downwards. So I have a point at pi over 2, 0, and then I have a point at pi, negative 1. I go back up here. This is what my graph looks like. You can just copy this. But I'm going up and down, continuing those periods. Oops, why? How did that happen? Okay, going up. And then here I'll have a point, here I'll have a point, here I'll have a point, and so I continued on the other side. Let me just make sure that's right. Going downwards, yeah. 1 period is 2 pi. Okay, so I did it right. And then I'm going to put in my vertical asymptotes. So this is not your graph. You can erase this at the end, but you can use it to help you to graph secant. So you can actually graph this graph, but know that it is not part of the graph for secant. Only the part in red is the graph for secant that I draw. I'm going to put my asymptotes in. So I have pi over 2 is 1. I have negative pi over 2 is another. I have 3 pi over 2 is 1. And then I have negative 3 pi over 2 is another. I have 5 pi over 2 is 1. And that is all I can fit on my graph. And then how I'm going to graph these is I'm going to look at the minimum or maximum, and I'm going to use the point that's at the minimum or the maximum. I'm going to use it to draw a parabola that is, as I go to the left, getting closer and closer to the asymptote. As I go to the right, getting closer and closer to the asymptote. So here in this case, I'm going to find the minimum, and I'm doing a downwards parabola. If it's a maximum, I'm going upwards. If it's a minimum, I'm going downwards. And this would have another asymptote here. Go downwards like this. This is a minimum, so I'd be going downwards. So what you're going to do, you're going to draw, so always draw y is equal to cosine of x for secant, and then use the maxes and minimums to plot secant of x as parabolas in opposite direction of what the cosine graph was. And then the last one, it's basically the same, is cosecant. So cosecant is the opposite of sine. I write it like this, CSC of x. I can also write it as y is equal to 1 over sine of x. And so I know I need to keep in mind that sine of x cannot be equal to 0. So whenever sine of x is equal to 0, there is a vertical asymptote. There is a vertical asymptote. So I have x is equal to 0 would make sine of x 0, sine of plus or minus pi is 0, plus or minus 2 pi is 0, plus or minus 3 pi is 0. So these are all not allowed to be 0 because they're in the denominator. Oops. Because they're in the denominator. So these are all vertical asymptotes. These are all vertical asymptotes. Then I'm going to plot this graph. I'm going to plot the graph of sine, and I'm going to use it just like it did for cosine. I'm going to use it, the maximums and minimums, to draw parabolas for cosecant. First, I'm going to label pi over 2, pi, 3 pi over 2, 2 pi, 5 pi over 2, 3 pi. This is negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. And then I'm going to put all of my vertical asymptotes in. So I have a vertical asymptote at x is equal to 0. I have one at pi. I have one at negative pi. Oops. I have one at 2 pi. I have one at 3 pi and negative 2 pi. And then I'm going to actually draw in black, which is not part of my graph, but I'm just going to use it as a guide. I'm going to actually draw sine. So I know sine starts at 0, 0. It goes up to 1, down to pi. I'm going to be at 3 pi over 2, negative 1, 2 pi 0, 5 pi over 2 comma 1, 3 pi comma 0. At negative pi over 2, I'm going to be at negative 1. At negative pi, I'm going to be at 0, 3 pi over 2 and 1. And then I'm going to connect these. Oopsies. I'm going to connect these, and I'm just using it as a guide. It's not part of my graph, so I can erase it at the end if I'm doing this in pencil. I'm using the maximum to go opposite direction of the sine graph, make a parabola that's getting closer and closer to the asymptotes on both sides. Here I'm using the minimum, so I'm going to actually be doing a downwards parabola like this. Here I have a maximum between these two asymptotes, so I make an upwards parabola like this. This is a minimum, so I'm making a downwards parabola like this. This is an upwards parabola since I'm using the maximum. And that's what my secant graph will look like. Just the red part. Just the red part. Just the red part is secant. So I can erase all of this other stuff. Now I can erase this as a guideline or as a guide curve. Yeah, it's not really easy to erase this. But this is the final graph, what it will look like.